Hi everyone, we are Sydney Group 28 and our project focuses on heart disease classification using machine learning and deep learning approaches. I am Masira, responsible for data preprocessing and traditional models, while my teammate Kisalka contributed Naïve Bayes deep learning and model aggregation. Together we developed a complete and end-to-end pipeline from data acquisition through model learning, evaluation, and final comparison. Heart disease is the world leading cause of death, with the World Health Organization reporting around 17.9 million deaths annually. Traditionally, diagnosis can be time consuming and resource heavy. In this project, we use machine learning and deep learning models to automate risk screening from 13 clinical features with a clear focus on recall to reduce false negatives that are most dangerous in clinical practice. This slide outlines our full pipeline. We structured the work into 5 phases: acquisition, pre-processing, training, evaluation, and aggregation. To ensure reproducibility, we automated all steps using the run all script, which generated models, metrics, and figures. Clear division of tasks between members allowed transparency, with member 1 handling pre-processing and traditional models and member 2 focusing on knife based and deep learning. This workflow ensured rigorous evaluation at each step. We use the Cleveland Heart Disease dataset from Kaggle, which contains 297 patient records, 13 clinical predicates, and target condition. After loading the CSV, we validated column names and inspected data types. The dataset is nearly balanced with 160 no disease and 137 disease cases, making it statistically valid for classification. As shown in the preview and the class distribution figure, this balance reduces bias and supports fair model training. In this step, we explored the dataset to understand feature ranges and distributions. Using pandas, describe, and histograms, we identified the mean as 54 and average cholesterol as 247. We also observed outliers in cholesterols and varying scales across features. These differences highlight the need for standardization to prevent one feature from dominating. The next step will be to study feature correlations. We analyzed predictor-target relationships using a correlation matrix. The heat map highlights that the chest pain type shows a positive correlation of 0.43, while maximum heart rate has a negative correlation of 0.42 with the target. This aligns with clinical expectations, building trust in our data. While linear correlations may miss complex patterns, this step confirms medically meaningful features and prepare us for pre-processing. At this stage, we prepared clean inputs for our models using an 80-20 train test split with 237 training and 60 testing samples. We applied a standard scalar pipeline to normalize numerical features. This ensured the fairness by preventing scale bias with no categorical variables and zero missing values. Pre-processing values was simple but crucial. The output saved as preprocessor and split files guarantee reproducibility and stable comparison across all models. For the decision tree, we trained a baseline model using scikit-learn classifier. The training was conducted on scaled data with five-fold cross-validation to ensure consistency. While simple and interpretable, the model shows instability across folds due to high variance, making it unsuitable as a standalone method. Next, we will look at the results. The decision tree achieved 80% accuracy with a precision of 0.83 and recall of 0.71, leading to a F1 score of 0.77 and ROC-AUC of 0.84. While the model was interpretable, it suffered from too many false negatives, missing around 3 out of 10 patients, which makes it clinically unsafe. Overall, the decision tree serves as a benchmark, but stronger models are required. Next, we will explore random forest. For the random forest, we trained an ensemble model using 100 trees on the scale dataset. To evaluate consistency, five-fold cross-validation was applied, giving a mean accuracy of about 0.82. Compared to the decision tree, this approach reduced variance and proved more stable, establishing random forest as a reliable baseline. Next, we will move on to the results. On the test set, the random forest achieved an accuracy of 83% with precision of 88% and recall improving to 75% compared to the decision tree. The F1 score was 0.81 and the ROC-AUC reached 0.92, showing strong overall performance. While slightly less interpretable, the higher recall and the ROC-AUC makes this model clinically safer as fewer patients are missed. Next, we will examine the precision recall curve and feature importance. This slide highlights random forest interpretability. Feature importance shows chest pain type, maximum heart rate, and thalassemia as the strongest predictors. Aligning with medical understanding, the precision recall curve confirms stable precision, while importance reflects contribution rather than causality. It adds clinical insight, making random forest both reliable and interpretable. Our collaboration was structured using Git and source tree for version control, Trello for workflow tracing, and MS Teams for weekly discussions. Each member worked in separate code files with outputs merged through a shared run or script. This ensured fairness, transparency, and reproducibility, though we occasionally faced sync delays. Overall, the process mirrored real-world data science teamwork, ensuring reliable outcomes. That concludes the traditional machine learning models. Next, we move to Naïve Bayes and deep learning approaches, which are expected to provide stronger accuracy and clinical reliability. Member 2 Kisalka will now continue with the Naïve Bayes, followed by multi-layer perceptron and LSTM models, building on the pre-processed dataset provided earlier.
I'm Kisaka, and my role focuses on Naïve Bayes, deep learning models such as multi-layer perception and LSTM, and final aggregation and comparison. My work builds directly on the preprocessing and random forest outputs prepared by Member 1 with the objective of pushing model performance further while ensuring clinical reliability. We train a Gaussian Naïve Bayes model using scikit-learn on the preprocessed dataset with 13 scaled features. The training followed an 80-20 split, and bootstrapping with 1000 iterations was applied to estimate confidence intervals. This provided a quick probabilistic benchmark, though limited by the independence assumption. Next, we will look at the results. Naïve Bayes model reached 86.7% accuracy with a strong AUC of 0.91. Precision was perfect at 1.0, but recall dropped to 71%, missing many disease cases. The confusion metrics and curves highlight this trade-off. Safe and avoid false alarms, but clinically risky due to false negatives. Next, we move to neural networks for improved recall and reliability. We train a multi-layer perception with 3 hidden layers of 128, 64, and 32 neurons using Adam Optimizer and binary cross-entropy loss. Dropout was applied for regularization to reduce overfitting, and the model was trained on 13 input features with an 80-20 split. Training converged in 37 epochs, showing more robustness than Naïve Bayes. Next, we will look at the ANN results. Multi-layer perceptron achieved 90% accuracy with high precision at 0.96 and recall at 0.82, giving an F1 of 0.89 and ROC-AOC of 0.96. The confusion matrix shows fewer missed cases, and the training curves confirm stable learning. Overall, the ANN demonstrated balanced performance, making it the most reliable model so far. Next, we extend this with the LSTM. We train an LSTM model by stacking two LSTM layers with the dense layers on top, reshaping the input to simulate sequential data. The training followed an 80-20 split and ran for 36 epochs, converging successfully without overfitting. While powerful, it is computationally heavier for static data. Next, we will look at the LSTM results. LSTM achieved strong results with 91.7% accuracy, perfect precision, and recall of 82%, leading to an F1 score of 0.90 and ROC-AUC of 0.95. The confusion metric shows 0 false positives and high recall, though it is more complex than ANN for static data. Next, we will extend the evaluation with precision recall and training curves. The extended result shows stable precision recall behavior, no signs of overfitting in the loss curves, and consistent accuracy across epochs. Training and validation stayed closely aligned, confirming strong generalization. Overall, LSTM demonstrated the best balance of recall and precision, though with higher computational cost. Next, we move to the final model comparison. This slide consolidates results from all 5 classifiers. This aggregated matrix was saved into a CSV and plotted as a group bar chart for direct comparison. We see that ANN and LSTM achieved the strongest performance overall, while random forest emerged as the best traditional model. This highlights the trade-off between interpretability in simpler models and the higher accuracy and the recall of deep learning methods. From a statistical perspective, this slide compares key metrics across all models. ANN and LSTM clearly outperform traditional methods, with ANN offering the best balance between recall and precision. Random forests stand out as the strongest interpretable baseline, while Naïve Bayes, despite perfect precision, suffers from weak recall. These results statistically validate deep learning as the safer choice for clinical deployment. From a clinical standpoint, recall is the most critical metric, as it reflects how many true disease cases were detected. Both ANN and LSTM identified around 82% of patients, which means 5 to 6 more lives could be saved per 60 cases compared to decision tree. While Naïve Bayes offered perfect precision, its misdiagnosis make it unsafe. Overall, deep learning models provide strong clinical reliability by reducing false negatives. After evaluating all 5 classifiers, the artificial neural network was identified as the best performing model. It achieved 90% accuracy and the highest ROC-AOC at 0.961 while maintaining balanced precision and recall. Unlike Naïve Bayes, it avoids unsafe misses, and compared to LSTM, it's more efficient to train and deploy. Overall, ANN offers the strongest trade-off between clinical reliability, safety, and practicality, making it the most deployment-ready model. To strengthen outcomes, future studies should prioritize external validation with larger multi-center datasets, introducing cost-sensitive training to minimize false negatives, and applying interpretability tools such as SHARP and LIME for greater clinician trust. These steps aim to improve generalization, robustness, and ultimately move to the system closer to the real-world deployment in healthcare environment. This concludes our recorded presentation. Thank you very much for watching.